All right, strap yourselves in because today we were going deep on virtual particles. And before we even start, I gotta say, forget those little like tiny billiard ball pictures in your head because that is so not what these things are about. They're much weirder and much cooler than that. And in this deep dive, we're not just going to talk about what they are, but we're going to see why they matter to you. And trust me, their impact is felt like everywhere, even in those crazy objects we call black holes.
Yeah, you know what makes them really, really interesting is they aren't like these little independent things. They kind of emerge from the fabric of reality.
Oh, okay. That sounds awfully abstract. Can we make this a little bit more down to earth?
So think about like a pond, a perfectly still pond. That's kind of like the vacuum of space, seemingly empty. But according to quantum field theory, even this emptiness is buzzing with activity. And particles are just like ripples in these underlying fields.
So the vacuum isn't really empty at all.
Exactly. And this is where Heisenberg's uncertainty principle comes into play. It essentially allows for energy to be borrowed from the vacuum for incredibly short periods. These temporary energy loans manifest as fluctuations in the fields, and those fluctuations are what we call virtual particles.
Okay, so they're not permanent residents of the universe,
Mhm.
but they kind of like pop in and out of existence. And while they're here, they can really shake things up.
Precisely. And their impact is felt in some of the most fundamental forces in nature. Let's take electromagnetism, for example. You might think that, like, two electrons repel each other at a distance. But actually, what's really happening is that they're exchanging virtual photons.
So it's not like they have some sort of invisible force field pushing them apart.
Nope. It's more like they're playing an incredibly fast game of quantum catch, tossing these virtual photons back and forth. And that exchange is what we observe as the electromagnetic force.
Oh, wow. So even something as basic as like the force between magnets
Yeah.
comes down to these fleeting virtual particles.
Right.
What other forces rely on this type of exchange?
Well, it's not just electromagnetism, the strong force, which is responsible for holding the nucleus of an atom together, also relies on virtual particles. These particles are called gluons. These gluons act like the glue that binds quarks together inside protons and neutrons. Without them, matter as we know it would simply fall apart.
Okay, so these virtual particles aren't just theoretical curiosities. They're actually like responsible for the stability of matter itself. I mean, that's pretty mind-blowing. But if they're so fleeting, how do we even know they're real? I mean, couldn't this just be some mathematical trick?
Not at all. There's experimental evidence that these quantum fluctuations driven by virtual particles have a real impact on the physical world. One compelling example is the Casimir effect.
The Casimir effect. Tell me more.
Imagine you have two metal plates, and they're placed very, very close together in a vacuum. You might think that there's nothing going on between them, but actually that space is teeming with virtual particles.
So even in a vacuum, there's this constant buzz of virtual particles popping in and out of existence.
Exactly. But here's the thing. The presence of the plates actually limits the types of virtual particles that can exist between them. It's kind of like they create a boundary for these quantum fluctuations.
Oh, so the plates are kind of acting like walls, restricting the virtual particle party.
Precisely. And this restriction has a measurable effect. The result is a force that pushes the plates together. It's a real, observable phenomenon that demonstrates the impact of virtual particles.
That's incredible. It's like the universe is constantly whispering to us, revealing its secrets through these subtle effects. But this kind of begs the question, if these virtual particles are so fleeting, how do we actually see them in action? It's not like we can just put them under a microscope.
Well, that's where Feynman diagrams come in. They're kind of a visual language for understanding particle interactions. They're not literal pictures, but they allow us to keep track of these fleeting exchanges, like a detective reconstructing a crime scene.
So instead of just describing these interactions with equations, we can actually like visualize them.
Exactly. And a visual representation is powerful, for instance. Feynman diagrams allow us to understand processes like electron-positron annihilation, where matter and antimatter collide and transform into pure energy. It's a way to see how these seemingly impossible events occur, thanks to the intricate dance of virtual particles.
So Feynman diagrams are like a roadmap for particle interactions, with these virtual particles acting as like hidden pathways connecting the players in the subatomic dance. But this raises another question for me. If virtual particles are influencing these tiny interactions, could they also be playing a role in like the largest structures in the universe, like black holes?
You're absolutely right, and that's where things get even more interesting. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. But even at the edge of a black hole, called the event horizon, virtual particles are hard at work.
Whoa, so even in the most extreme environments, these quantum fluctuations are still happening. What's going on there?
This is where we encounter Hawking radiation. Picture a pair of virtual particles popping into existence near the event horizon. One of these particles might get sucked into the black hole, while the other escapes into the wider universe.
So one gets trapped and the other escapes. What happens to the one that escapes?
That escaping particle effectively becomes real and carries away a little bit of the black hole's energy.
Wait a minute. You're saying that black holes aren't completely black after all. They're slowly losing energy and evaporating over time due to these virtual particle shenanigans.
That's the current understanding. It challenges our classical assumptions about black holes. It suggests that even these seemingly invincible objects are subject to the whims of the quantum world.
This is incredible. So virtual particles are involved in everything, from the tiniest interactions between particles to the fate of giant black holes. I'm hooked, but I have a feeling the ability to scratch the surface. What else are these elusive particles up to?
Well, get ready to go even deeper. Because next we're going to explore how virtual particles shape our understanding of everything from supersymmetry to the Higgs field, and even the nature of space-time itself.
All right, now you're just teasing me. Don't worry, we'll be back soon to delve into those mysterious realms. But for now, let's all take a moment to digest the incredible things we've learned about virtual particles so far.
So are you ready to jump back into the quantum realm?
Absolutely. Last time we left off, you were hinting that virtual particles might be involved in things like supersymmetry and the Higgs field. Those sound pretty intimidating. Where do we even begin?
Let's start with supersymmetry, or SUAY as it's often called. It's a pretty crazy idea. That proposes that every known particle has a hidden superpartner particle. So think of it like each particle has a secret twin, but it's much heavier.
So like a whole other set of particles just waiting to be discovered? Why? What's the point of having all these extra particles?
Well, one of the big reasons physicists are so excited about SUSY is that it could solve some big mysteries in particle physics, for instance. It might explain why gravity is so much weaker than the other fundamental forces.
Yeah, that's always been a head-scratcher. Why is gravity such a weakling compared to the electromagnetic force or the strong force?
Yeah, it's one of the biggest open questions in physics, sometimes called the hierarchy problem. And SUSY offers a possible solution. But here's where virtual particles come in. Even though we haven't detected these hypothetical superpartner particles yet, we can use virtual particles to predict their behavior, if they do exist, how they might interact, how they might decay.
So it's like we're using our knowledge of virtual particles to hunt for clues about these hidden superpartners.
Exactly. By studying the subtle effects of virtual superpartner particles in our experiments, we might be able to indirectly detect their real counterparts. It's kind of like using shadows to infer the shape of an object.
That's a clever approach. So even though these superpartners are hiding out, they still might be leaving behind these telltale virtual fingerprints. What about the Higgs field? You mentioned that virtual particles play a role there too.
Yes. The Higgs field. That invisible field that permeates all of space and is responsible for giving particles their mass. Virtual particles are constantly interacting with the Higgs field, causing it to fluctuate.
So I'm picturing this Higgs field like a vast, calm ocean.
Yeah.
And these virtual particles are like tiny ripples disturbing its surface.
Yeah, that's a good analogy. And these ripples, these quantum fluctuations, actually have an impact. They can influence the mass of particles and even affect the stability of the Higgs field itself.
Whoa, so the very essence of mass is tied to these fleeting virtual particles. That's amazing. But you also mentioned something even more profound, quantum gravity. What role do virtual particles play in this grand quest to unify quantum mechanics and general relativity?
Now that's where things get really wild. Quantum gravity aims to bridge the gap between the world of the very small, which is governed by quantum mechanics, and the world of the very large, governed by Einstein's theory of general relativity.
Right, because so far those two theories haven't been getting along very well. What's the holdup?
Well, one of the biggest challenges is understanding how gravity behaves at the quantum level, and virtual particles might be a key part of this puzzle. One idea is that space-time itself might be made up of countless virtual particles, constantly popping in and out of existence, creating what's sometimes called quantum foam.
So instead of thinking of space-time as this smooth, continuous fabric, it's actually this frothing sea of virtual particles. That's a pretty big change in perspective.
It is. And if this quantum foam picture is correct, it could have some big implications. It might explain how gravity works at the tiniest scales, giving us a deeper understanding of black holes, the Big Bang,
Mhm.
And the nature of reality.
Okay, I need to take a deep breath. We've gone from virtual particles influencing the stability of atoms to potentially shaping the structure of space-time itself. But before we completely lose ourselves in the quantum abyss, can we bring this back down to Earth for a second? You hinted that virtual particles actually have applications in technology too.
Absolutely. Understanding virtual particles isn't just some abstract thing. It's actually really important for advancements in fields like quantum computing and cryptography.
Okay, now we're talking. I've heard a lot about quantum computers lately. How do virtual particles fit into that?
Well, quantum computers rely on the principles of quantum mechanics, things like superposition and entanglement, to carry out calculations in ways that classical computers can't. And guess what? These quantum phenomena are deeply intertwined with virtual particle interactions.
So by harnessing the power of these fleeting particles,
Hmm.
we might be able to build computers that are way more powerful than anything we have today.
Exactly. And it's not just quantum computing. Virtual particles are also important in the development of new types of cryptography, which could lead to much more secure communication systems.
It's amazing how something that started as a theoretical concept in physics is now finding practical applications in all these cutting-edge fields. It's a testament to the power of fundamental research. But I have to ask, what's next in this adventure of understanding virtual particles? Where do we go from here?
Well, the quest to understand virtual particles is far from over. Exciting new research avenues are constantly opening up. For one, new particle accelerators, like the proposed Future Circular Collider, will allow us to smash particles together at much higher energies, potentially revealing new insights into virtual particles and how they interact.
So we're talking about recreating conditions like those just moments after the Big Bang,
Mhm.
right here on Earth. What might we find in those extreme environments?
That's the exciting part. We might find new particles, new forces, even gain clues about extra dimensions. It's a journey into the unknown.
Okay, you're really pushing the limits of my imagination. But it's exciting to think that we're on the verge of unlocking these incredible secrets of the universe.
And it's not just about particle accelerators. Advancements in astrophysics and cosmology are giving us new tools to study virtual particle effects on a grand scale, for example, by analyzing the cosmic microwave background radiation, which is the afterglow of the Big Bang. We can learn about the role that virtual particles played in the very early universe.
So it's a multifaceted approach, with physicists and astronomers and cosmologists all working together to solve this puzzle. It's a testament to the collaborative nature of science and the human desire to understand our place in the universe. But I feel like we could go on for hours about virtual particles, so maybe it's time to wrap up this part of our deep dive.
And think about what we've learned so far. I feel like we've been on this amazing journey.
Through the quantum realm, we started by exploring how virtual particles mediate forces, and then we saw how they affect black holes. And now we're even talking about how they could shape the structure of space-time itself.
Yeah, it really is incredible how these things we can't even observe have such a huge impact on how we understand the universe.
It really makes you wonder what real even means. Like if these particles are influencing everything around us all the time, it's like reality is kind of fuzzy.
Yeah, that's a really deep question, one that physicists and philosophers have been thinking about for a long time. But maybe that's part of what makes the quantum world so interesting. It challenges us to change how we think.
Absolutely. So for anyone who's just joining us on this deep dive into virtual particles, what's the one thing you hope they'll remember?
I think the most important thing to remember is that virtual particles aren't just some made up thing. They have real effects on the world around us. They influence the stability of atoms and the behavior of black holes, and maybe even how the universe is expanding.
And, as we learn more about virtual particles, who knows what amazing discoveries are waiting for us? It's a field with so much potential for breakthroughs, like in quantum computing and new forms of energy.
Exactly. Studying virtual particles really shows the power of just being curious. Even if we can't directly see these particles, their influence is everywhere, driving innovation and pushing the limits of what we know.
I like that. So as we wrap up this deep dive, I want to leave everyone with one last thought. We've seen how virtual particles are part of some of the most fundamental processes in the universe, from tiny particle interactions to the life cycle of black holes. But here's the question. If these fleeting invisible things are so basic to reality, what does that tell us about existence itself? Is everything we see just a result of these quantum fluctuations?
Now, that is a question. That'll probably keep physicists and philosophers busy for a long time. It makes us rethink what's real and what isn't.
It reminds us that the universe is full of mystery and wonder, and that there's always something new to learn. So keep asking questions, keep digging deeper, and stay open to the possibilities. Until next time, happy exploring.